Recording in progress.
So, hello everyone, and welcome to this fifth week. So, we are in the fifth week of this course on essential mathematics for machine learning. And before we begin, just a few logistical details for those of you who are joining for the first time. These sessions are held every week on Saturday at 3 p.m. So it's a 1 hour session from 3 p.m. to 4 p.m. every Saturday. And in these sessions, our aim is to solve previous year's assignment problems, and they will in turn help you to understand the concepts and solve the current year's and the current session's assignment problems. So some people have been asking me personally to solve the questions from the current session, and let me be very clear that we are being told categorically that we are not supposed to solve the assignment problems of the current session. Why? Because, well, it is obvious, because the current session's assignments are being graded, so they are being used to assign a grade to you, some marks to you, and at the end of the course, if you give the assignments, all the assignments and the mid-sem and sem exams, then you would receive a certificate of completion with your marks and your grades mentioned over there. So we are not supposed to solve the current session's assignment problems, and I want to be very clear in this. I have been receiving repeated requests to solve the current session's assignments, and I'm really sorry, but I would not be able to do that for you. So what our aim is to do rather is to solve the previous year's assignment. So just like you prepare for any exam, you solve the previous year's question papers, right? So that's the aim of these live sessions, that we solve the previous year's assignment problems, and hopefully they would help you to solve the current session's assignment problems. And just some details for those of you who are joining for the first time. We have a YouTube channel where all these sessions are live streamed. And thing is that either you could join in the Zoom and watch it, or you could go to the YouTube live stream and watch it. And the YouTube video would be there forever. So even if you miss some session, or if your network connectivity is not good, you could go to the YouTube channel, you could and then watch the video. So you could subscribe to the channel, and you would get notifications every time we upload some video over there. And the other thing that we have is a Google Drive folder. Uh, in this folder, we upload all these lecture notes. So let me just share the folder with you. So you could bookmark this Google Drive folder, and in this folder, we upload the all these assignment problems that we are solving. And some of you had requested me to upload the lecture notes that I prepare, apart from the ones that the instructors upload. So I have started uploading some of the lecture notes. So week 5's lecture notes are uploaded on the Google Drive. So yeah, so I also prepare some very simple, very brief, very short lecture notes, not as elaborate as the instructors upload. These lecture notes are basically for my reference, that I would use to prepare these assignment, to prepare the solutions for these assignment problems that are there. So yeah, if you want, you could have a look at them as well, and they are pretty much condensed. So yeah, so those are my lecture notes which I upload on this same Google Drive as well. So let us begin with today's session. So today we will be discussing week 5 assignment problems. So of course from the previous year. So as you know, the current session week 5 is going on, and you are required to upload your week 5 assignment solutions in a few days from today. So let us begin. Our first question is that if the sum of squares of the residues and the sum of squares of the total residues are equal, then what is the value of r squared? Now this question is very simple. Only some technical jargon they have used, and I would remind you of what the equation for r squared is. So we have let us say if we have an equation for curve fitting, linear regression, or whatever curve fitting that we want to do. So if we have the equation where of the form that y is equal to some alpha, some constant, times some beta times the input variables, which are x. Now this beta x, this x could actually be a bunch of variables, x1, x2, x3, and so on. So correspondingly, you would have beta 1, beta 2, beta 3, and so on. But the form is like this. Your output variable is some constant times multiples of the input variable. So in this, you define R squared quantity. What is R squared quantity? It is basically goodness of your fit. You can think of it as a goodness of your fit. How good is your fitting model that you have come up with? So R squared is defined as 1 minus sum of square residuals from the model with both alpha and beta included, divided by sum of square residuals from the model with alpha only. So this is the definition of R squared that we have, and higher the value of R squared, it would mean that better is your fitting. And if R squared value is low, that means your fitting is very poor. And R squared basically ranges from R squared ranges from 0 to 1. 0 meaning absolutely useless fitting, like it's useless, it's not at all good. And 1 meaning it is perfect fitting. So somewhere a value is about, let's say, a 0.9 would mean that you are doing very good with regards to your fitting function and the fitting parameters that you have obtained. So this is the definition of R squared. Now in this, these jargons that are written in the question, so this term right here, this numerator, is what they mean by, sorry, I should go back to my original color. So yeah, this is what they mean by SSRES, that means sum of squares of residuals. And this bottom, this denominator right here, okay, let me, so this denominator over here is what is given as SS total. So sum of squares of the total residuals. That is what they mean when they are writing this SS. So it's just the short form technical jargon that they are using. And this is what it is. So if the numerator and denominator are same, that means this ratio would become 1. And 1 minus 1 would mean 0. So the answer would be 0 for the first case. So pretty much simple question based on the formula for R squared, which measures the goodness of any fitting parameter. Now let us move to the next question. By the way, this assignment is also quite simple and quite small, quite short, I mean to say, because in this week also we have had Python implementation of the concepts. So many of the questions are based statements regarding Lasso regression and ridge regression. Now I will write it down for you. So in Lasso regression, we use L1 penalty, meaning to compensate for the overfitting, what we use is the term lambda mod of alpha j. So mod of alpha j is like an N1 penalty. But in ridge regression, what we use is the L2 penalty. Where what we use is lambda times alpha j squared. And what these alphas are, well, this is just y is alpha naught plus summation of alpha j xj. So Lasso, we use mod of alpha j for compensating for that overfitting that we some overfitting problem that was discussed in the lectures. And ridge regression, what we use is alpha j squared. So alpha j squared means L2 penalty, or the L2 norm is being used, and mod of alpha j means that L1 penalty or the L1 norm is being used. So let us look at these statements one by one. Lasso regression helps in knowing the important features of the model. This is a true statement. Lasso regression indeed helps us in feature selection. Next statement is Lasso regression uses L1 penalty same as the ridge regression. Now this is wrong. Why? Because Lasso regression indeed uses L1 penalty, but ridge regression does not use L1 penalty. Ridge regression uses L2 penalty. So it is not same. Lasso regression and ridge regression are not same. They do not use the same penalty. And then ridge regression results in non-sparse solution. That is true because Lasso regression is the one which results in the sparse solution. So now next question. This is a question based on the Python implementation. So the question states, from sklearn.pre-processing, importing standard scalar helps in which of the following tasks? Now the correct answer is answer number A. I will explain it. So standard scalar makes the mean value 0 and scales each of the features to unit variance. That means it makes it shifts the data. So you have some input data that you have for each of your features. You would have let's say 4 or 5 features, and then you would have data corresponding to those features. So what the standard scalar does is that it shifts your data so that your mean becomes 0. So if you have data points like 1, 5, 3, 6, 8, 10 or something like this, all positive numbers, what will happen is that it will shift about the mean. So some data points would be negative, some data points would be positive, such that your mean becomes 0. And the second thing that it does is that it scales your data such that your standard deviation becomes 1. So if you have data points which are integers 1, 2, 3, 4, 5 like this, then it will scale it to fractional decimal points such that your standard deviation of your data set becomes equal to 1. So this is the correct option, and as you can see, all the other options are pretty much bogus. Standard scalar gives unit mean and scales each feature variable to 0 variance. Now this is absolutely useless. Like if you scale everything to 0 variance, that means there is no variance. So each of your value is exactly the same. If the value is 5, then you have 5, 5, 5, 5, 5 repeated n number of times. So that's useless. That is not a distribution at all. So next statement says standard scalar makes both the mean and variance 0. Again, I said making 0 variance is absolutely useless. Option D says standard scalar gives unit mean and scales each feature to unit variance. This also does not make sense. You do not want to make your mean equal to 1. You would want to shift it so that you get your mean to be equal to 0. Now I will just write down the basic syntax that is used to basically implement this standard scalar. This is given in the lectures. So from the lectures only I'm writing, but I'm just writing it down over here for the sake of completeness. And then you would have these lecture notes as well, so you can just go over the syntax for using the code. So yeah, so in this week and in the previous week also, we have had lectures in which the instructors are discussing the Python implementation of the topics and the theory stuff that we are learning. So it is important to learn the theory concepts as well, and then to finally implement the theory concepts learned in Python. So knowing both is important. Just knowing the Python is not going to help you if you do not know what functionality you should be using. So you need to know the theory in order to be able to solve your problem with the right tools. And just knowing the theory is also not going to help, because you need to know how to implement it, or implementing the theory. So I'm just writing down the syntax. So this standard scalar would be from sklearn. It is in the sklearn package. So sklearn dot pre-processing. From this, what you would do is you will import standard scalar. And then you would create an instance of this standard scalar like so. And what this will do is this will make the mean of your data 0 and the standard deviation of your data as 1. And then you would use this command to basically implement it. So this fit underscore transform is the one which will finally implement it. So over here, you are just creating an instance of the standard scalar, and then you are using it in the second line to implement that standard scalar on your data. And once you have implemented it, then you can go to your regression. With that scaled data that you have, you will apply the regression models on the scaled data. Let's say this logistic regression we want to apply. So it is a classification problem, logistic regression. And then you are using the class fitting with your data sets, and then you would predict whatever prediction you want or classification you want based on this predict command. So the important lines which are governing standard scalar are these three lines. So this is how you would implement the standard scalar to transform your data and to shift your data with mean 0 and standard deviation 1. So next question. Again, it is a question based on Python implementation. So the question says, which of the following is correct for dividing the data for training and testing purpose, considering the scalar utility? So we have seen this in quite a few lectures, that we have a big data set, and what we do is we split that big data set into two parts. One part we use for training our whatever classifier we have, our training model that we have, and the other part we use for actually testing. So we will run the classifier on the testing after training it, and then we will see whether it is able to classify the thing correctly or not, or whether it is able to predict the values correctly or not. So that is the utility of splitting the data into training and testing data sets. So the correct option in this is part A again. So what you use to split your data set is from sklearn.model selection, you import train test split. So like over here I have written, so I will copy paste this statement over there. So this is the syntax that you would use for splitting your data into two parts. So what this means is that you are splitting your data set, and this number over here, this 0.25, means your testing size is 25% of your entire data set. So 75% of the data you are using to train your model, and once it is trained, then you are testing it on 25% of the data points, and then you are trying to see how accurately you are able to predict your results. So this is a very helpful feature. You would typically want to use this functionality quite often, because you want to use some data for training and some data for actually testing your models. So next we proceed to the next question. This is question number 5. So considering the sigmoid function, so we are given the sigmoid function. So in the theory lectures, we were given the sigmoid function, which is like an S-shaped curve. Which of the following is not true? So we are given some statements regarding the sigmoid function, and we need to check the validity of the statements. So the sigmoid function is bounded in this domain. So it lies between 0 and 1. And since it lies between this 0 and 1, it is bounded because it has a bound. It has a lower value and an upper value, lower limit, upper limit, and all the values lie in between. So you can see that if x tends to negative infinity, then your sigmoid function tends to 0. And if x tends to positive infinity, your sigmoid function tends to 1. Now let us look at the derivative. So it is infinitely many times differentiable. This is a true statement. We can find out the derivative. So let us find out the derivative of the sigmoid function. So this is the first derivative, and you can keep on differentiating it as many times as you want because of the presence of this e to the power minus x. So exponential functions can be differentiated any number of times. So there is absolutely no discontinuity anywhere. So that is what it means. So let us now try to simplify this. So this can be written as follows. Now this term right here is nothing but our sigmoid function. So this is sigmoid function times this part. Now this part we can write it as follows. We can add and subtract 1 in the numerator. So we are adding and subtracting 1 in the numerator. And what this does is that we get the following. This gives us 1 minus 1 over 1 plus e to the power minus of x. Now again, this thing right here, this term is nothing but your sigmoid function. So what you get is s of x times 1 minus s of x. So that means the derivative of the sigmoid function is sigmoid function times 1 minus the sigmoid function. That means option number C is incorrect because plus sign is written over here. Had it been negative sign, this would have been correct. And let us just for verification see that the last statement is true or not. So s of minus x would be e to the power minus of minus x, that is e to the power positive of x. So now 1 minus s of minus x is the following. Just simple algebra. And then we will divide both the numerator and denominator with e to the power x. That would give us the following, which is nothing but the sigmoid function itself. So this last statement is true. So the only untrue statement is statement number C, which would have been true had this sign been negative. Moving over to the next question. Which of the following is correct for creating a logistic regression object? So this is again a Python based question, and the correct answer is option number D. We would use sklearn dot linear underscore model dot logistic regression for the logistic regression. Now I will just write down briefly the syntax. We have seen this earlier as well. So in the lectures, you would see that how to implement this. So briefly, I'm just writing down very simple code, 3-4 lines. Then we will create a classifier of this logistic regression. And then we will fit the data. And then we will predict the outcomes based on the fitting. So simple code that you would be using. Now next question, for a linear system ax equal to b, where a is of the order 7 cross 11, the number of free variables is, so we are given these options. Okay, someone has asked some question regarding some previous question. Is sigmoid function continuous everywhere? So yes, Manideepa, sigmoid function is continuous. There is absolutely no discontinuity. So it is a completely smooth function that we have. It is continuous everywhere, it is differentiable everywhere, and it is differentiable up to any order that you want. First derivative, second derivative, nth derivative. You can keep on differentiating it any number of times that you want. So yeah, coming back to this question. So we are given a 7 cross 11 matrix. So let me just create a dummy 7 cross 11 matrix. So 1, 2, 3, 4, 5, 6, and 7. So 7 rows and 11 columns. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have a 7 cross 11 matrix that we have. So out of this, so 1, 2, 3, 4, 5, 6, 7. So 7. So when you apply the method of for reduce the row operations to reduce this into the reduced row echelon form, so you want to solve the system of linear equations ax equal to b. So what you do, you basically apply row reduction operations to reduce the matrix into the basically the augmented form into a reduced row echelon form. So this would be your matrix A, and you would apply row operations on this matrix A as well as on the column vector B, same operations, and then you would obtain the reduced row echelon form. Now in the reduced row echelon form, your diagonal elements would be 1. So each of these diagonal elements, now how many diagonal elements you would have? You would have 7 of these because you have 7 rows. So you would have this a pivot as they are called. So these elements are called pivot, and in reduced row echelon form, above and below the pivot the values are 0, and all over here in the reduced row echelon form it will be 0. So how many free variables you have? The free variables are these, the ones which do not have a pivot. So variables which do not have this pivot 1 are called the free variables, and as you can see you have 1, 2, 3 and 4 of them remaining. So you have 4 free variables. And how this is coming? This is coming from 11 minus 7, which is equal to 4. So the correct option is option C, which is 4. You have 4 free variables. Next up, we have some questions on finding the pseudo inverse of certain matrices. So we are given this matrix A. So for m cross n matrix, so you know, if you have a square matrix n cross n, you can find out the inverse of the matrix. But if you have a rectangular matrix, some m cross n matrix, you cannot find out its inverse in the traditional sense that we find out the inverse. What you can find out is only the pseudo inverse. And for pseudo inverse, if you have m cross n, and if m is greater than n, then the pseudo inverse is given as follows. Over here, this dagger operation signifies pseudo inverse, and if m is less than n, then you have the pseudo inverse is given as follows. And this is our case, because in our case what we have is we have m equal to 2 and n equal to 3. So our case is that of m less than n. So let us find out. So let us first find out A transpose. So this is the matrix A. Then we have the transpose of the matrix A. And then we will multiply it. So this is A transpose. And then inverse of this. So A transpose inverse. Now inverse of a square matrix is very simple. You find out the determinant. So 1 over the determinant. Determinant is 2 into 4 minus 1, 3. So 4 minus 1. And then you switch the diagonal elements. Both are same over here. So it remains 2, 2. And then you multiply negative 1 to the off diagonal element. So this is your inverse. And then finally the pseudo inverse would be A transpose times A transpose inverse. So this is A transpose, and this is A transpose inverse. So this is the answer. So let me see which option is correct. So it turns out option number D is the correct option for the pseudo inverse. Next, we have a question based on the least square solution of the overdetermined linear system. So, you know, if you have n linear equations and n variables, you can find out a proper unique solution to those system of linear equations. But if you have n variables, but more than n equations, so let us say you have 5 variables but 10 equations. So this is what is called an overdetermined linear system. So we are given an example of an overdetermined linear system where we have 2 variables but we have 3 equations. Now the solution to this is what is known as the least square solution. So it is like an approximate solution which minimizes the error. So it is not an exact solution. You cannot solve it exactly. You can only solve it approximately, and you can make sure that you are minimizing your error. So you are being very close and very accurate to your solution. So this is the overdetermined system. So overdetermined linear system. is given as follows: Ax equal to b. Now in our case, our A matrix is this coefficient matrix. So 1, 1, 2, -1, -2, 4. X is the variable matrix, x1, x2, which we need to find out. And B is the constant. So this is 1, 2, 7. Now the solution to this overdetermined linear system is given as follows. So this is nothing but, if you know, this term is pseudo-inverse times b. So this A dagger that is written over here is the pseudo-inverse. And this right here is going to, this x equal to A dagger b is your least square solution. So let us find out A transpose A. So this is A transpose, and then A. This is the following 2 cross 2 matrix. So inverse would be, as I mentioned earlier, for a 2 cross 2 matrix, 2 cross 2 square matrix that we have, the inverse is very simple. You take the determinant. So 1 over determinant. Determinant is nothing but 9 into 18 minus this 9 into 9, which is 81. And then you interchange the diagonal elements. So it becomes 18 and 9. And you multiply -1 to the off diagonal. So they become +9, +9. So this is the inverse. If I do this arithmetic, 18 into 9 minus 81, this gives me 81. And this is the inverse. Now let us multiply this with A transpose. So plain simple arithmetic it is. Just make sure you are doing the multiplications properly. Otherwise, there is chance of doing some calculational error. So 18 into 1 plus 9, that's 27. 18 into 2 minus 9, that's again 27. And then 18 into -2, that's -36, plus 9 into 4, 36, that makes it 0. 9 plus 9, 18. 9 into 2 minus 9, that's 9. 9 into 2, 9 into -2 plus 9 into 4, that makes it 18. So I see that these are multiples of 9, so I can do some simplification. I can take factors of 9 common. So this would become 1 by 9, because I'm taking 9 common from within and from outside. So 9 into 3 is 27. So I'm taking 9 common. So this is the thing. And finally, the solution would be x is the following. Sorry, I wrote this here incorrectly. It should be like this. A transpose A inverse A transpose times B. So this is 30212, this times your column vector B. So 1 by 9 times 3 into 1 plus 3 into 2, that is 9. Then 2 plus 2 plus 14, that's 18. Again, taking 9 common, you get 1 and 2, which is nothing but 1 and 2 transpose. So the correct option is option B right here, transpose of 1, 2. Then moving over, last question. again Python based implementation. So in Python, dataset.head helps in what? So the correct answer is A. It helps in getting the top 5 data samples of the data set. So as you would have seen in the lectures, uh, what we do to import our data set is to use the following syntax. Then we will upload our data set. And then we will select whatever file we have on whatever data set that we want. So from here, we will select and upload the file from our computer. And then let us say it is a data set of some students' mark sheets, some scores. So what we will do is we will read the file that we just uploaded, the student scores. Sorry, not CVS, it is CSV. CSV format file is there. And then what you do is you would just use score.head, and then it will display some amount of data along with the column and row headings. So in your CSV file, you would have had some column and row headings, like let's say student name, student roll number, student marks, students class. So all those headings will come in the top, and then serial wise serial number would be there for row numbers, so 1 2 3 4 5, like that. And then this some amount of data is actually 5 samples. So 5 samples would be displayed. So this is the correct option, and this PD comes from import pandas as PD. So this is the pandas library. So this is the basic syntax. So dataset.head gives you the first 5 data elements, and you can use this to basically confirm that you have uploaded the correct data set, just to see some data elements from there and see that the features are correctly mentioned and it is indeed the data set that you want, and you can see what feature elements are there and the number of feature vectors that are present. So that's all for this assignment. It is a pretty much simple assignment, largely based on the Python implementation. So you should definitely watch the Python implementation lectures. Uh, this is so Python implementation is present in week 5, lecture 3 and lecture 5. So these are the basically Python implementation, and you can go ahead and watch those lectures. And I have written uploaded this week's lecture notes, that I have prepared on the Google Drive as well, and you could go ahead and check those. If there is any error, I have tried to proofread it, because when I am preparing my notes I was not so much careful, but before uploading I've tried to proofread it. But if still there is some error, please do let me know. You could put it up on the YouTube channel, or you could put up a comment in the YouTube channel if there is some error in any of the topics. So I'm providing the link to the YouTube channel once again in the chat box for those of you who joined late. So that's our YouTube channel, and that's the Google Drive folder where you will find all the lecture notes and the assignments. So yeah, that's all for today, and see you over in the next week, Saturday 3 p.m. So thank you everyone. So Thomas Hooder, are you there? Like, could you please unmute yourself? Thomas Hooder, if I'm please correct me if I'm pronouncing your name wrong. It seems that you are the host now, so you would have to stop the recording and close the meeting for everyone. I got disconnected for some time. As a result of this, you have been made the host. So, Thomas Hooder, are you there? The others could leave. So, Manideepa and Suresh, you could leave if you do not have any doubt.